By Newton's second law, we know F is equal to ma. Okay, so whenever there is a force, there is an acceleration expected. So when we talk about gravitational force, that means there must be some acceleration due to gravity as well. That is what we are going to find out here, that how do we calculate this acceleration due to gravity. So for that, what we are doing here is we are assuming that suppose this is a mass capital M. Say in our case, since we are going to be bothered with Earth most of the times, let this be representing the Earth. Okay, so this is the surface of the Earth with mass capital M, with radius capital R. Okay, and suppose an object is falling towards it with mass capital small m. Okay, so this is a mass capital M. Let this be the Earth. It has a radius capital R, and a mass small m is falling towards the surface of the Earth. Now, when this mass is just about to reach the surface, just about to strike, okay, at that instant, if I write the forces acting on this object, they will be, by Newton's law of gravitation, they will be written as F is capital G, gravitational constant, times the product of the two masses divided by the distance between their centers. Okay. Now, if I put the values, specific values in this case, according to Newton's law of gravitation, I am putting here the value of the two masses as capital M and small m. So F becomes capital G, capital M divided by small m divided by, when this object is just about to strike the surface of this earth, इनके बीच का distance कितना हो जाएगा? Radius of the earth square approximately. Okay. Now this is one form of the force that is acting on this object. According to Newton's second law, which says F is equal to ma, I can write the force on this object small m as F is equal to m into a. Okay, I am replacing a here by small g. Why? Just to indicate that it is acceleration due to gravity. So I am replacing this a by g because small g is representing acceleration due to gravity. This object is freely falling और कोई force इसके ऊपर act नहीं कर रही है, सिर्फ gravity is acting on it. Okay, so I am referring it to as small g. Okay, so this becomes F is equal to mg. This is equation 2. Now I am talking about the same object and the same force acting on the object. इस ऑब्जेक्ट के ऊपर फोर्स सिर्फ इस मास कैपिटल एम की वजह से लग रही है और कोई फोर्स नहीं है. ओके, सो इसका मतलब ये दोनों फोर्सेस इक्वल है. सो व्हेन आई इक्वेट 1 and 2, what do I get? When I equate 1 and 2, I get F is G capital M small m divided by R square, and also F is small m into G. Okay, the common term small mass goes away and I am left with an expression for acceleration due to gravity small g as gravitational constant, mass which is attracting the small m divided by the radius square. Okay, so this is the mathematical form of acceleration due to gravity. Okay, it depends on the gravitational constant, the mass of the earth or the planet or the celestial body जिसकी सरफेस पे हम एक्सेलरेशन ड्यू टू ग्रेविटी निकाल रहे हैं, और उसी सेलेस्टियल बॉडी का उसी मास का रेडियस स्क्वायर. ओके, so you can clearly see this acceleration due to gravity is independent of the mass which is falling. Okay, so that would mean even if 1 kg mass is dropped or 1000 kg mass is dropped, the acceleration on that mass will be the same as offered by the surface of the earth or any other celestial body for that case. All right, small m is not in picture when we calculate small g. इसका मतलब क्या है? जब हम किसी भी ऑब्जेक्ट को ड्रॉप करेंगे सरफेस ऑफ द अर्थ की तरफ, तो लाइक सपोज आई हैव दिस चॉक पीस एंड आई एम गोइंग टू रिलीज इट, आई एम गोइंग टू ड्रॉप इट, तो जीरो वेलोसिटी से ड्रॉप होना शुरू होगा ये, और धीरे धीरे इसकी वेलोसिटी इंक्रीज होगी, किसकी वजह से? ड्यू टू ग्रेविटी. Alright, now if instead of this chalk piece of few grams, if I would have dropped some substantial weight, say a 10 kg mass, it would have also fallen with the same acceleration. जितनी acceleration से ये 5 या 10 grams की chalk गिरी है. Okay, the acceleration due to gravity is independent of the mass which is being dropped or which is falling or on which the gravity is acting. It is independent of the mass. Okay, you can clearly see here स्मॉल जी के फॉर्मूला में स्मॉल m का कोई रोल नहीं है. किस प्लैनेट की वजह से स्मॉल जी लग रहा है? उसके मास का, उसके रेडियस का रोल है. Okay, so talking about acceleration due to gravity, this is the formula that we had derived, that small g is capital G capital M upon r square, and you can clearly see we had reiterated this thing many a times, that small g is independent of the small mass that is falling towards the surface of the planet we are talking about. Okay, now for Earth, if we calculate this value, that is when an object is near the surface of the Earth, when I put these values for Earth, the parameters for Earth, the mass of the Earth, the radius of the Earth, and the value of gravitational constant, which is a universal constant, I get the value for acceleration to gravity as 9.8 meter per second square. Now, we were discussing the meaning of this statement. It means that when an object is freely falling near the surface of the Earth, okay, like I was giving an example, if I drop this chalk from the top floor of a building, after 1 second, the speed will be 9.8 meter per second. After the next 1 second, it will be plus 9.8. So 9.8 plus 9.8, it will become 19.6. Okay, and another, after the third second, it will be 19.6 plus 9.8. Okay, is this thing clear? That would be somewhere around 29.4. Okay, so plus 9.8 meter per second होती जा रही है speed या velocity to be specific where an object is freely falling. That is what is the meaning of acceleration due to gravity. Okay, so the value near the surface of the Earth we have calculated as 9.8 meter per second square. The question is that imagine a planet with mass twice that of Earth and the radius is same that of Earth. You have to find the value of small g on that planet. Okay, no other data is given to you. Alright, it's only that you need to keep in mind that small g on the surface of the Earth is 9.8 meter per second square. This is the only data that is given, that small g on the surface of the Earth is 9.8 meter per second square, and you have to calculate the small g value on that planet. Okay, so we have to find the value for small g on that planet. The formula for small g that we have derived is capital G capital M upon r square. Capital G is the universal gravitational constant, M and R are the values of mass and radius of that planet. ओके, जिसके ऊपर हम जी कैलकुलेट कर रहे हैं. ठीक है, तो पहले हम अर्थ के लिए ये फॉर्मूला लिखते हैं जो कि ये है. हमने यहाँ बस जी ई कर दिया इसको जस्ट टू डिस्टिंग्विश कि ये जी अर्थ की बात कर रहे हैं. ठीक है, और अगर हम प्लैनेट पे यही वैल्यू लिखेंगे जी की तो कैसे लिखेंगे? कैपिटल जी तो सेम रहेगा विच इज कांस्टेंट थ्रू आउट द यूनिवर्स. मास की जगह क्या आएगा? ट्वाइस एम, क्योंकि अर्थ का मास अगर आप एम डाल रहे हो तो इसका मास ट्वाइस एम डालो, और रेडियस सेम, रेडियस स्क्वायर. Okay, so this is the equation for the acceleration to gravity on that planet. Okay, now if I have to find the value of g on that planet, I will have to divide these two equations so that the common terms go away and I am left with only a constant. Okay, so g on that planet is twice gm upon r square. G on Earth is gm upon r square, where m is the mass of the Earth, r is the radius of the Earth. The common terms go away and I am left with only a constant 2 in the numerator. So g on that planet is coming out to be twice of g on Earth, cross multiplying, twice of g on Earth. Okay, or I can rewrite this as g on planet is twice g on Earth. हम कितना लेते हैं? अभी हमने कैलकुलेट किया था 9.8. So g on that planet is coming out to be 19.6 meter per second square. So that is the value of G on this imaginary planet. 19.6 meter per second square. I hope the calculation steps are clear to all. Okay. What have we calculated? We started from the formula for G. G on Earth is Gm upon R square. G on the planet will be G twice the mass of Earth upon R square, because the radius of both are same. It is given in the question. Okay. Then dividing both these equations, I get a relation between G on planet and G on Earth. It comes out as G planet is twice G on Earth, and G on planet, by putting the values of G on Earth, I am getting as 19.6 meter per second square. So it is on the similar lines. Another question which says that you have to find the acceleration due to gravity on a planet whose mass is twice that of Earth and the radius is half that of Earth. You are only given the acceleration to gravity on Earth. Alright, so following the same steps now. Small g on Earth, we already know the formula is Gm upon R square. Okay. For that imaginary planet, G will be as it is, M will be replaced by twice M, and R will be replaced by R by 2. And we are going to put a whole square on this term. That is a common mistake which students make. They only put a square on R and 2 is as it is in the denominator. So that creates an error in the calculation. Okay. So be careful, it has to be R by 2 whole square. Okay. So now opening up the brackets and simplifying, it becomes 2gm divided by R square by 4. Okay. So this R square by 4, this 4 will go in the numerator. Okay. So that becomes 8gm upon R square. Okay. Now simply comparing these two equations, or if you divide these two equations, that is up to you how you comprehend the answer. If you divide Gp, G on the planet divided by G on the Earth, it becomes 8gm by R square upon Gm upon R square. Okay. So common terms Gm upon R square go away. We are left with only 8. And when we cross multiply, this implies that G on the planet will be 8 times G on Earth. Okay, so that becomes, how much will that be? That will be 8 into 9.8. Okay, so this becomes 78.4 meter per second square. So this is the G, small g value on that imaginary planet, 78.4 meter per second square. Okay. Okay, so how does the value of G vary from equator to poles? Remember, the shape of the Earth is not a perfect sphere. Okay, it's flattened near the poles. Okay, so if these are the axes, you can see that near the poles, the Earth is a bit flattened. Hence, the radius of the Earth is not constant. The distance here, I can say the radius along the poles, and the distance here, the radius along the equator, is different. Okay. On the conclusion is that radius along the poles is less than the radius along the equator. That is because of the shape of the Earth. It's not a perfect sphere. It's oblate. Okay. It's flattened near the poles. So due to this shape, the radius along the poles is less than the radius along the equator. And when we talk about small g, which is Gm upon R square, if I now compare the small g value on poles, which will be Gm upon R near poles square, and G near the equator, that will be Gm upon R equator square, where it will be EQ, so that there is no confusion. Okay. Now when I compare, आप देखो इस वाले फ्रैक्शन में डिनोमिनेटर छोटा है, न्यूमरेटर दोनों में सेम है, जिसका डिनोमिनेटर छोटा होगा उसकी वैल्यू ओवरऑल फ्रैक्शन की ज्यादा होगी, Okay, so looking at these values and keeping this inequality in mind, we can conclude that G on poles is greater than G near the equator. Okay, so this is how it varies. When we go from equator to poles, the value of small g increases. Okay, small g increases when we go from equator to the poles. When we go from equator towards the poles, the value of small g increases. Reason being, Earth is not a perfect sphere. Okay, it is flattened near the poles. The radius near the poles is less as compared to the radius near the equator. Okay, and hence due to this inequality, we know the formula of small g is d1 upon r square. So when I put the values for radius along the equator and radius along the poles, I can compare and see that g near the poles would be greater than the g near the equator. Okay, so that means if you are dropping an object near the equator and you are dropping the same object near the poles, it will be accelerated more when it is falling near the poles. Okay, reason being, acceleration due to gravity is more there. Okay, so the next definition that we are discussing is that of free fall. And when we say an object is freely falling, when the object falls freely under the action of gravity alone. Now, in the chapter motion, we have discussed the equations of motion as v is equal to u plus at, s is equal to ut plus half at square, and v square minus u square is 2as. We had discussed these three equations in the chapter motion, and using these equations we have also calculated these variables depending on the data given. Now specifically in this chapter we will be dealing with freely falling objects, when objects are dropped from a height, okay, or an object has been thrown up. So after throwing, only gravity is acting on it, okay, assuming that no air resistance is there. Okay, so these equations will be modified. How? Because in these equations now, instead of A, we are going to replace them by G. क्योंकि अब एक्सेलरेशन की जगह एक्सेलरेशन ड्यू टू ग्रेविटी होगी अगर हम फ्री फॉल वाला केस कंसिडर करते हैं. So now, in case of numericals where the object has been dropped or an object has been thrown up with a velocity, the equations when you use for calculation, you will be replacing A by G, small g. Okay. Displacement might also take the place here. Instead of displacement, we can here mention heights. कितनी height gain करी है या कितनी height से drop की. Okay, so in books you will find कि displacement की जगह यहाँ h लिखा हुआ है, height लिखा हुआ है. Okay, so don't get confused. It is the same equation. It is only mentioning कि displacement vertical directions में हो रही है क्योंकि तो हमने height से उसको replace किया हुआ है formulas में. ठीक है? So this is the change that will happen when the equations are being used during free fall.